In this video, we're going to talk about 3.4 Objective 2, where we construct and compare time series graphs and exponential graphs. So first, what is an exponential scale and when is such a scale useful? So an exponential scale rises by powers, otherwise known as exponents. That's where it gets its name, usually, but not necessarily powers of 10. An exponential scale is useful when there is a huge range of data values. We can have exponential growth that looks like this, or exponential decay that looks like this. So lots of times we use this type of a graph with population growth. For instance, we might use something like this for radioactive decay, something along those lines. You're probably mostly going to see this type of exponential curve here. And if you want to learn more about those, you can look at some of the videos that are for Math 154 or for Math 161 that discuss those topics a little bit more. But the answer here is C. Question 2, Moore's law refers to a prediction made in 1965 by Intel co-founder Gordon Moore, who suggested that the number of transistors on computer chips would rise exponentially with time. With some variation, the prediction has held true for decades. Use the accompanying table to answer parts A through C, and the table is down here. And we see in 1971 there were 2,300 transistors on the circuit board, and then in 1972 there were 3,600, and then in 1974 there were 6,100, and we see this trend to where in 2020 there were 30 billion 100 million transistors on the circuit board. So we would have a very hard time graphing 2,300 and 30 billion 100 million on the same y-axis without turning these into scientific notation and graphing these on an exponential scale. So which of these is showing a rising curve that's roughly exponential? And that would be B here. Now, one of the things that we can use to try and make this scale, this thing that's exponential, look somewhat more linear is to use something called a logarithm. And it's basically what they've done here in the next part, but construct an exponential graph of these data in which the subdivisions on the vertical axis are powers of 10 here. So 1, 10, 100, 1,000, and so on. And when we do it that way, then instead of everything being of the order of magnitude of 10 to the 10th, we change the orders of magnitude as we go up. We get this line. It looks like a line instead, like D. Okay, and so which of your two graphs is more useful for these data, and explain? The graph in part A gives you a better picture of the true nature of the rate of change, so that's exponential. The graph in part B makes it easier to see the change in the early years because it's just really hard to see all these data points that are close together down here in the early years and estimate those changes. It's a little easier to see them spaced out here on this scale here. So again, this is a relationship between exponential functions and logarithmic functions that we're not going to explain in this class, but that you can investigate further if you want to look into the quantitative reasoning and pre-calculus part 1 topics. All right, that is it for this video, and we will come back next time and talk about 3.4 objective 3. See you for the next video.